Next speaker is Professor Lan Chung, Professor of Dankook University. He will talk about development of an active mass damper for reducing wind-induced vibration of super-tall buildings.
Thank you, Mr. Chairman. And I am very happy today to have a great opportunity to present my recent research, development of an active mass damper for reducing wind-induced vibration of super-tall buildings. This project is a part of grand project which is supported by Korean government. So at the first part, I'm going to introduce my grand project, and the details of this research will be presented by Professor Sang-hyun Lee, who is a co-researcher of this project. So let me introduce my research center. The title is Super-Tall Building Design and Engineering Technology Research Center. And the other part will be presented by Professor Lee. Well, the title of this grand project is Development of Technologies for Super-Tall Buildings, established in Dankook University. And this project consists of 4 subjects. The first subject is integrated design of complex shaped building conducted by Chang Min-wook structural consultant. And the second title of subject 2 is energy saving and eco-friendly technology, which is conducted by the Seoul National University. And the third project subject is performance improvement of a structural system conducted by Dankook University. And the last subject is smart float platform technology, is undergoing on by the Kyungwon University. Those subjects consist some small topics, such as you can see this. And today we are going to present this topic. And the total budget of this huge project is about 30 million US dollar. And the research period is about 6 years. And the number of organizations involved is 27. And the number of major researchers involved is 66. The objectives of this center are develop world-best technologies and green technologies and integrated technologies. Let me introduce a brief contents of those subjects. The first subject is integrated design of complex shaped building. It consists of the 3 major topics. The first topic is optimization technology for complex shaped structural system. The purpose of this topic is to develop practical methods for seismic design and evaluation of complex shaped tall buildings, and so on. You have this material in your USB. So let's just explain the brief. The second topic of subject 1 is integrated platform for complex shaped structural system. The purpose of this topic is to develop infrastructure for computational design and evaluation method for the structural system of complex shaped tall buildings, and so on. The third one is open BIM information environmental technology, developing open BIM-based standards for management and QA for super-tall buildings, and so on. The second subject is energy saving and eco-friendly technology. Consists of two topics. The first topic is hybrid renewable energy system. The purpose of this topic is to develop optimized design and the construction technology of a hybrid energy system and the others. The second energy subject is low energy indoor environmental control system. Is to develop prefabricated heating and cooling radiant panels applicable to super tall office buildings, and so on. The third subject, which the title of Performance Improvement of Structural Systems, consists of 4 topics. The first topic, which will be presented in next speaker, wind-induced vibration control technology. The purpose of this topic is to develop domestic technology of designing and manufacturing of wind-induced vibration control dampers. As you can see, the test specimen of damper, and so on. The second one is integration of vibration control and the computerized platform. Is to develop world top-class technology by addressing wind-induced vibration control system to computerized platform, and so on. The third one is progressive collapse prevention and anti-terrorism, to develop automation technology for progressive collapse analysis and design of complex shaped super tall buildings, to developing something. The last subject, which is smart photon technology. The first topic is power grid and the system integration technology. The purpose of this topic is develop a platform of gridable building systems for super tall buildings, and some others. And the second and the third one, this subject was started about a couple of months ago only, so the results are not gathered so far. Well, this was my brief explanation of a grant project which is conducted in Korea and supported by Korean government. The details of this wind engineering in Korea will be presented by Professor Lee. Please.
Thank you, Professor. Since I am practically in charge of the wind-induced vibration control, I'll proceed the remaining presentation. Unfortunately, before this project had begun, there is low self-reliance in the field of wind engineering. So, for an example, in the application of active mass damper 2 at Ulsan Air Hotel in Korea, the damper hardware, such as mass, motor, and rail, and spring, etc., was manufactured by domestic, such as Korean engineering company. As you know, the automobile industry of Korea has world top level class of name, so the hardware could be easily manufactured by domestic engineering company. However, the damper software, such as controller, and which has embedded control algorithm, is totally manufactured by foreign engineering company. Furthermore, the engineering fee paid for the two works are significantly different. So we all think that how can we overcome these difficulties? All the projects are conducted like this. So we are focused on to develop the controller development for AMD or HMD. The second goal is to integrate the wind vibration control and structural design optimize and modeler, of which name is so-called STRAUTO. I want you to remember the name of STRAUTO. The STRAUTO is the target for our research center to develop to world top class level engineering technology. The STRAUTO can conduct a model very conveniently. Three target is optimal design of a structure with dampers, and accurate wind load estimate and input, and third, model update technique based on monitored wind-induced vibration data. Since the accurate wind load estimation and input is so difficult, so we are trying to make an input model for the complex shape building structures. And then, as you know, the monitored building data, such as frequency or damping noise, are significantly different in some cases for the ones obtained by the structural analysis models. So we are developing a model updating model based on the monitored wind vibration data. I will show you some details about STRAUTO. STRAUTO can arbitrarily change the building height and position outrigger damper or outrigger position and the shape of the mega column inclination. In some cases, we have made much time effort in general software program. However, using the STRAUTO, this structural model can be easily conducted. I think this model can be obtained within an hour. So we are developing this STRAUTO as a top level technology, we think. As a first step, we develop software development for analysis of a structural damper system. As an input information, the structural information such as mass, stiffness, and damping is given by STRAUTO. And then wind load, earthquake load is input. And damper design information is finally given, mass ratio, position, and numbers. And then we can obtain output information automatically. First, damper design result. We can obtain for respective damper, TMD, TLD, TH, and HMD can be obtained. And then the controlled result, such as structural response, for example, difference, velocity, acceleration can be obtained. Another advantage of this software is we can express the effect of control result, effective damping ratio, and wind load reduction effect. This figure shows with increasing mass ratio and the damping ratio obtained by damper is increased. As you can see that the activeness damper obtain highest damping ratio when the same mass ratio is used. This slide shows the result, the integration of the software and the STRAUTO. You can see that the damper effect is expressed in terms of effective damping ratio and wind load reduction factor. And then the structural model, such as core thickness and outrigger position, is redesigned by using STRAUTO. All these design results was obtained within only 1 hour. So we can think that the STRAUTO and the software we developed can make a great progress in design of super tall buildings with dampers. Of course, the concrete quantity and the cost by the structural member can be automatically obtained. This is the first prototype model of active mass damper. This is damper itself, and this is the controller, in which the control algorithm is embedded. As you can see in this figure, the experimental results and analysis results are almost the same. So we can expect that damper behaves as we expect. For the verification of the damper performance, we conducted the post-vibration test and free vibration test. The damper with 40 kilogram of mass is mounted with a pendulum type moving mass of which mass is 2 tons. The effective damping ratio has increased from 1.6% to 8%. You can see that the damper behaves as we expected. This figure, this video clip shows the controller is off when the controller is on. The moving mass is excited by human excitation. When the controller is off, the building oscillates continuously. I said to my students to excite this moving mass with the same strength of amplitude. They did it. I expect it, and the performance of the damper can be verified. We have focused on the development of control algorithm. Generally, linear control algorithms such as linear quadratic regulator, linear quadratic Gaussian, H2, H infinite are widely used. The linear control algorithm is known to have good stability and good robustness. Besides, nonlinear control algorithms such as collapse optimal, slide mode control, and reap control. Nonlinear control algorithm is known to show good control performance. We are now focused on the development of new control algorithm, which has both good performance and stability. The goal is the damper reduce volume, weight, and price by 25%, and further increase damping performance by 10%. If this is possible, we can have the brand name. The damper brand is low-cost, compact, wind motion damper. Nonlinear control algorithm is developed based on the Rayleigh probability distribution of structural energy. First, the state space is first formulated, and then mean and minimum structural energy obtained by using observer. And then Rayleigh probability distribution of structural energy can be obtained. The magnitude of control force is said to be proportional to the probability the current structural energy will exceed the threshold of the specified energy. And the direction of the control force is to be set for the damper to decrease or absorb the structural energy. As you can see this equation, if the force, the sign of force, control force is said to be the opposite to the lambda, it can play a role of dissipating structural energy. And now we have a plan to apply this damper to the Songdo Northeast Asia Trade Center. The Songdo Northeast Asia Trade Center has height of 305 meters. Its story is 68 floors. The building is originally planned for the usage of office. However, the owner lately has changed his mind. We want that building should be used, can be used for residential usage. So, as you know, the acceleration level for the residential usage is much more higher than just for office. We are now considering the damper usage. Fortunately, we can find the place for the damper installation. At 65 floor, which will be used for lounge, we can find the space beside the core, 6 by 6 meters. This slide shows the time schedule for the pilot test. This year, wind vibration data is being monitored, and the acceleration level in practical application is checked. Next year, test tower will be constructed, and the performance of the proposed damper will be finally checked. And then practical damper will be installed to this building. And 2014, the performance of the damper movement and the building response will be monitored. In simulation results, the wind load in y direction may cause excessive acceleration response in this direction, in across wind direction. Higher aspect ratio may induce higher vibration in across wind direction. This wind load is generated based on the power spectral density function of the was obtained by wind tunnel test. This figure shows you the good agreement from both one. Firstly, AQR controller was designed for the comparison with the proposed control algorithm. Effective damping ratio was increased by 4% and peak acceleration 5.4 GAR. Maximum control force was 110 kilonewton and maximum stroke was 1.5 meter. This is the result from proposed controller design result. The equivalent controller performance to LQR. As you see that the acceleration response show good controlled response. The acceleration controlled by proposed algorithm and by LQR is almost same. However, the maximum control force is required by proposed algorithm is only 60 kilonewton, which is 55% of 100 kilonewton required by LQR. And then maximum stroke is only 1 meter, which is 67% of that required by LQR. So we can, all these results were obtained by just numerical analysis. We expect that if we can realize in practical situation, we can have the brand name, it's low-cost compact damper. Now I am introducing you ongoing research. First, the second prototype model is being produced. It is possible to control multimodal and it can adapt control force to wind load amplitude. For example, when the amplitude of wind load is small, linear control logic applied, and the amplitude of wind load is strong, nonlinear control algorithm will be applied. And then displacement feedback algorithm based on GPS monitor data are being considered. Another topic, as I mentioned earlier, is integration of wind-induced vibration control and STRAUTO. In this step, we are developing 3 modules. Wind load input module for complex shape building, and second, optimal design model for a building stroke with damper, and third, model updating model based on monitor wind-induced vibration data. Now it's the concluding remarks. The Super-Tall Building R&D Research Center in Korea was briefly introduced by Professor Chung. And the post-phase research software for optimal design and analysis of damper installed tall building and the first prototype active mass damper were developed. 3. Pilot simulation results from 6-day tall building with the proposed damper showed that the proposed control algorithm could show better performance than the existing one. Especially, it requires very much smaller installation space. We can say that it may be called as compact damper. Second phase research for low-cost compact damper are under process. Thank you. Thank you very much.
Any question? Okay. Thank you for your good